Our modern world is full of colour, and almost every shade is available to us, manufactured and ready for use.
As human beings, we seem to be born with the need to represent our world through art.
Modern science has provided us with a rich, vibrant palette of paints. Deep blues, beautiful greens, flaming yellows. We have these thanks to a quest for colour which began 15,000 years ago and gave us everything from these magnificent cave paintings in France
To Tutankhamun's treasures in Egypt.
and the Alhambra in Spain.
But how have we managed to progress from just a few basic shades to the riot of colour we have today? As a geologist, I'm going to show you that it's all down to an understanding of what's beneath our feet. The answer's here, in the rocks.
Our quest for colour begins here in France's Dordogne region, at the caves of Lascaux. These are among the first images ever painted. They came to light in 1940 when some children caught in a storm stumbled in here. What they discovered had been hidden for 15,000 years.
These cave paintings here at Lascaux show us that from very early on, humans went to great lengths to recreate the world around them.
The images on the cave walls are a sort of Stone Age menu. Reindeer, wild boar, all the food that early man hunted for survival. But why, when catching food for our ancestors was a matter of life or death, did they take time away from the hunt to paint these?
Well, one theory is that Stone Age artists believed that if they painted a picture of what they fancied for dinner, it would give them a better chance of catching it.
Which, if it were true, would have made the effort of painting it nearly as important as the hunt itself. These paintings, for our ancestors, may well have been a sort of giant good luck token.
It's all very lovely, but from a modern perspective, isn't it a little bit lacking in colour? Even a wee bit dull. I mean, these artists are trying to picture the world. Where's the blue of the sky or the green of the grass? Why limit yourselves to reds and browns? The answer is in my lunch.
Here's a perfect place for my picnic, Roussillon in the south of France. It's also an ideal spot to explain where the cave painters found their colours.
Think of this mug of soup as a world. Right now it's a swirling mass of ingredients, but as it cools down, things separate out.
The heavier pieces fall to the bottom, some linger in the middle, and the lighter ones rise to the top.
That's what happened when the Earth was formed, 4.5 billion years ago. Still hot from the processes that formed it, the planet began to cool down.
The heaviest materials sank to form a dense core. The stuff that wasn't as heavy, the mantle, stayed in the middle.
The lightest material rose up to the surface to form the crust. It's about 70 kilometres thick, and it's here that the cave painters found their colour. It may not look like it, but this is the Stone Age equivalent of an art shop.
These reddish rocks are called ochre. They're a combination of iron and oxygen, and they're abundant in the Earth's crust. These iron oxides have been a source of artists' pigments for thousands of years. Artist David Atkinson brings his students here to paint with colours literally scraped from beneath their feet. Wow. Where
I
are the
mean,
rocks then?
So I'm just looking at colour. And in fact, you don't actually need paint to paint here because the colour is all around us on the ground.
This is your palette, is it?
Yeah. It's a mixture of sand and the ochre pigment.
Yeah.
And depending where you take it from, you know, it goes from very dark, and down here, you know, we're actually just really a pure yellow ochre. So you can just physically use that and mix it either with some kind of oil to make an oil paint, or you can mix it with gum arabic to make a kind of watercolour paint.
So you wouldn't use blood or urine or something like that? Because that's what I heard the cave artists, that's what they used to use. But
they did, and animal fat.
All right.
You know, but it's all actually the same method. You're taking a natural pigment and you're using some kind of a glue to stick it on the paper. So we've got the actual stuff here on the ground, and you can just scrape a bit out with a palette knife. Then you just got water, a bit of binder, and you've got paint.
So the first painters used whatever they could get their hands on. And luckily for them, nature had provided some basic colours at the surface. The ochre for the reds and yellows. And another crust material, a combination of oxygen and manganese, was perfect for the browns. For the whites we saw in the Lascaux caves, they used natural chalk. Whilst the blacks came from the charred remains of sticks from their fires.
With just a few basic colours, our Stone Age ancestors set out to represent their world, and perhaps to improve their chances of a decent meal. Their paintings weren't intentionally dull, they were making the best of what was available to them. Our cave painters didn't know that they were literally just scraping the surface. They were too busy staying alive to discover that, as well as their reds and browns, the earth had a whole lot of wonderful colours. It would take 10,000 years and a civilization obsessed not with dinner but with death to unearth this new palette of colours.
Egypt. Thousands of us come here every year, drawn to the rich sights and sounds of this colourful country, which was home to one of the first great civilizations. One which transformed the rocks on its doorstep into the most breathtaking monuments. And there are no better examples of this than the pyramids. The Sphinx, the temple at Karnak, and the tombs here at Luxor. There are about 400 of these tombs dotted around the west bank of the Nile. Each one containing the colourful stories of life and times in ancient Egypt.
Look at these paintings! It's incredible to think that all this detail had survived for 3,000 years. But what amazes me most is the colours. I mean, look, here's the browns and reds and blacks and white that we saw in the caves in France. But look, over here, we've got bright yellows and oranges and greens and blues. Compared to the cave paintings, these are positively psychedelic. But what was it that made the artists who painted these go to all this trouble? Particularly when the tombs would be sealed and the only visitor was dead.
The ancient Egyptians believed that the world was created from chaos, and life was a constant battle against the descent back into that chaos. And as believers in life after death, they were desperate to make sure that their afterlife would be orderly and completely chaos-free too.
These pictures of bountiful harvests and healthy, happy people going about their daily business aren't how life really was in ancient Egypt. They're how the ancient Egyptians wanted life to be after they were dead.
These images were a kind of insurance policy and needed to be as realistic as possible. Which was why getting the right colours was so important. greens to paint the lush vegetation, yellow to paint the sun, and, most important of all to a civilization that depended on it, blue to paint the life-supporting Nile. But where did they get this richer palette?
Fortunately for the Egyptians, thanks to a chain of geological events, the colours they needed were actually right on their doorstep. Remember my soup? How when the Earth was forming, the lighter materials ended up near the surface to make the Earth's crust? Well, along with the iron and manganese oxides that gave the cave painters their reds and browns, there were other materials in the crust. And it was those that held the key to the ancient Egyptian colours.
When the Earth was first formed, these colours weren't concentrated together like the chunks of red and brown rocks we saw in France.
Instead, they were scattered in tiny amounts throughout the crust. Getting hold of them would be like trying to pick out the individual grains of sugar in this cake.
But over millions of years, those particles were brought together in concentrated form, so they could be used by the ancient Egyptian tomb painters. To show you how that happened, I'm going to travel back 30 million years. This lava lamp may not be 30 million years old, but it does help to explain how the ancient Egyptians got their colours. The light bulb in the base of the lamp heats the wax, making it expand and rise towards the surface. This is exactly what's happening deep beneath our feet. Heat trapped inside the Earth from when it was formed causes a rock in the mantle to get hotter and expand. As it expands, this plasticky molten rock forces its way up into the crust, moving very slowly, just a few centimetres a year. As it pushes up, it causes the crust to crack. And it's these cracks and fissures which are crucial to the whole process, because they provide places for the colour particles to collect. To show you how the colour collects in those cracks, I'm going to need some help from a few handy tourists.
The people down there are common crust minerals, but scattered amongst them, too small for us to see, are tiny scraps of colourful materials. Excuse me, can you help me do some geology?
No, thank you.
Oh, no, okay. Excuse me. I know this sounds really daft. Can you put that green hat on and just stand up?
The green hats represent particles of copper, which is only present in minuscule amounts, as little as 14 parts per million, scattered throughout the Earth's crust.
And I'll...
The essential ingredient, at least 2 million, also managed to drink in some culture by visiting this, the wonderful Alhambra Palace. It was built by some of Spain's first visitors, ones who stayed not for a 2-week holiday, but for 7 centuries. The Arabs. Originally from the Arabian Peninsula, they were on a mission to spread the word of Muhammad. They conquered much of the Middle East and then travelled west along the North African coast, arriving in Spain in 711 AD.
This is fantastic. It's one of the world's most amazing buildings. But from my geological perspective, the Arabs left behind something far more important than beautiful architecture. And the clues are all here in the art.
When I look at these complex geometrical designs, I see a civilization fascinated by science and maths. The Arabs produced these designs using knowledge they'd picked up and developed from countries around the Mediterranean. By the time they reached Spain, over 1,000 years ago, there was one particular idea that they had acquired on their travels which they thought might just hold the key to making gold.
And it was the ideas of the Greek philosopher Aristotle that they found especially interesting. He was one of the first to attempt a scientific explanation of how our world was made. And he thought it came down to just 4 substances: air, earth, fire, and of course, water. That theory, if true, meant that all the materials on the planet came from combinations of those 4 essences, as he called them. So, logically, you could use those 4 ingredients to make any of the materials on the Earth.
Armed with Aristotle's ideas about the world, the Arab alchemists set about putting them to the test.
They were convinced they now understood how to carry out the ultimate transformation, something that would have made the Egyptians green with envy, to turn dull, useless rock into beautiful, valuable gold.
And here in Almaden, in central Spain, they appear to have found the perfect rock to effect that transformation into gold. Almaden was a working mine for over 2,000 years. Today, it's in the safe hands of ex-miner Angel Hernandez.
This is 300 years. This is it, yeah?
Yes, here it is.
Oh, look at that.
Look.
Yeah. And right all over. This is it. This is what I've been looking for. Cinnabar.
It doesn't look much like gold, but it does sparkle. And this must have caught the attention of the Arab scientists. They wondered whether cinnabar contained similar proportions of the 4 essences of gold. If they could recombine the essences in slightly different proportions, then maybe they could make gold.
But first, the Arab alchemists had to unmake the rock.
Cinnabar is a combination of mercury and sulphur. To make gold, the Arabs thought they would need to extract the mercury and recombine it again with the sulphur using different proportions.
So we've got our lovely cinnabar, but how did the Arabs get the mercury out?
First, they breaking in a small piece like this,
Okay.
and after crush it.
Oh, okay. So you crush away at this to break it down into smaller and smaller pieces. And then what? What next?
They cook in the furnace at about 300 degrees centigrade.
300 degrees centigrade. And that would bring out the mercury.
Yes, like this.
God, it's heavy, isn't it? That's amazing.
Yes, and look, liquid.
That's incredible. When you see it like this, it's not surprising that the alchemists thought they would get gold. I mean, this is weird stuff.
Yes.
Weird, yes, but not the gold they were after. Whatever combination of mercury and sulphur the Arabs tried, they still couldn't achieve their ultimate goal.
Alchemy was founded on a fundamental mistake. All the materials of the world are not made of essences. The Arab alchemists had failed to make gold, but they did manage to make something that in its time and weight for weight was nearly as valuable. When they heated mercury and sulphur, they made this, VerMillion.
During their experiments to make gold, the Arab chemists had focused on some of nature's most colourful rocks. The results were greens, yellows and rich, vibrant red. These colours were embraced by artists and soon spread around the Mediterranean. For the next 400 years, the colours the Arabs discovered in their labs transformed the once limited artist's palette into a rainbow of different colours. By the 16th century, Renaissance artists like Veronese were using just about all of the colours then available.
It's beautiful. But to me, it's so much more than just a picture. It's like a geological map revealing the secrets locked up in the rocks. I mean, it's amazing to think that all this comes from rocks. This is iron oxide, ochre. It's one of the colours used by the cave painters, and it's still here 15,000 years later, scraped up from the ground to produce these reddish browns. Malachite, the rock that we first saw in Egypt, which is made by hot water scavenging its way up through the Earth's crust. It's here, in these greens. And this is VerMillion, that vivid red colour that the alchemists created from mercury and sulphur found in cinnabar.
These were exciting times for Renaissance painters. The development of these colours provided a whole new impetus for artists. They started to mix their pigments with oil rather than egg or water, which helped them achieve greater shade and tone. This, along with the greater range of colours, allowed artists to paint subjects in a much more real and rounded way. Lifelike flesh tones, subtle hair colours, and drapery so good you could almost touch it.
But there was one more rock that helped artists to make their pictures even more realistic. But that would take a few centuries and several wars between England and France.
Paris, famous for its culture, its architecture, and fashion. However, it wasn't always such a romantic destination. By the end of the 18th century, the city had played host to a bloody revolution and seen thousands die in wars with England that lasted on and off for nearly 50 years.
With all that fighting, both sides were always on the lookout for that winning advantage. And the secret weapon would be a rock, graphite. Unfortunately for the French, the best graphite was in England. The English arms manufacturers discovered that instead of casting their iron cannonballs in sand, graphite moulds were much better.
The balls from the graphite moulds were so smooth they flew out of the English cannons faster and travelled further. Graphite became invaluable to the English military campaign. But its properties also came to the attention of artists. It wasn't a colour as such, but artists saw its value as a revolutionary new tool. Graphite is an ideal drawing material. It's portable, doesn't smudge easily or run when wet. It makes strong dark marks, but more importantly, can be used to create shade and depth.
The reason graphite is so good for drawing lies in the way that it's made. Imagine this wafer is a lump of graphite. You can see that I can pull the layers apart. There's very little holding what's above to what's below. And that is exactly how graphite's made. Graphite has lots of sheets of carbon atoms that are joined together horizontally, but which have very few vertical connections between the layers, which means that the layers can slide over each other, and explains why graphite is soft and slippery.
This makes it not only good for making really smooth cannonball moulds, but also ideal for pencils. As it's dragged across the paper, the layers are pushed off, leaving a clean, hard mark behind. It seemed, in the War of the Pencil, that the French were to be the losers. They, like the rest of Europe, had only low-quality deposits of this fantastic material and were forced to pay a very high price to the English who controlled the supply. But in 1794, a French inventor called Henri Conté managed to strike a surprise attack and deal the English a decisive blow.
Conté discovered that by mixing low-quality graphite with clay, he was able to make a pencil that was much better than one made of pure high-quality graphite. Remember all those HBs in art class? Well, the H tells you how much clay there is. The higher the H, the lighter the mark. And the B's tells you how black it is. The more B's, the more graphite, and the darker the mark.
The combination of this new product gave artists much more flexibility, and they didn't have to pay the English for the pleasure. In fact, pencils like the one Conte invented dominate the market today.
So it's thanks to cannonballs, artists finally got hold of the perfect material for drawing realistic pictures. Can I see what it is, Leah? Can I have a look?
Yes,
Can I have a look?
yes,
Thanks.
Finish. Yes.
Oh, excellent. You make me look pretty.
Oh, thank you so much.
You've made a small nose as well. I'm forever grateful.
With the pencil, new techniques, and the colours from the Arab alchemists, the artists were better equipped to represent the world as they wished. However, there was a problem. The colours contained a major flaw. The very paints used to create these masterpieces also threatened to destroy them.
If we look again at Veronese's masterpiece, we see it's not actually as colourful as he originally intended.
Down here, in the corner of the painting, the dwarf's clothes have faded. The jacket and trousers were originally deep blue, but unstable paint has meant the blue has virtually disappeared. On Veronese's The Marriage Feast at Cana, the results haven't been disastrous. But in some cases, the paints have faded or corroded, destroying the vivid colours that the artist had used. Worse still, the paintings contained a dark secret. The paint itself is lethal. The white here contains lead, and the orange realgar, arsenic. Artists were working with deadly substances. And possibly the most famous casualty of colour was none other than the French Emperor, Napoleon himself.
Napoleon, do you know how he died?
Shortage of breath?
Shortage of breath. That's a good one. How Napoleon died. Do you know?
Well, I think it's much argued about, isn't it? Because, I don't know, he was old, I don't know.
Like falling into an iceberg?
Falling into an iceberg. That's fantastic.
No, I don't know.
Died of oxygen.
Was it Napoleon that committed suicide?
I didn't go to school for that long, I can tell
Well, you could guess how people die.
I don't know, he was shot or something.
Shot.
Did Josephine kill him?
You guys have a camera crew out here to figure out how Napoleon died?
Yeah. It's now suspected that what finally brought an end to France's greatest general was colour.
Following his defeat at the hands of the English, Napoleon was exiled here, on the bleak island of St Helena. The house has since been redecorated, but the original wallpaper was painted with a green pigment. A Swedish chemist, Schill, made the green colour by mixing copper sulfite with copper arsenide. In damp conditions, the arsenic in the paint could react with the air to give off a poisonous vapour. Nearly 200 years after his death, Napoleon's hair was tested. Residues of arsenic were found, which confirmed that he was exposed to this toxic gas. Already sick with a stomach ulcer, it's thought that this may well have hastened his demise. Colour, it seems, could kill, and artists took great risks with the paints they chose to create beautiful paintings. But something was about to happen that would revolutionise art and make colour non-toxic.
I By the time Napoleon died in 1821, chemists had already begun a series of discoveries that would eventually produce colours that were long-lasting and safe. And like the alchemists before them, this new breed of chemists weren't looking for colour. Their experiments were driven by the demands of the Industrial Revolution. But the results would create some of the most remarkable art the world had ever seen. And it was all because of this. Air.
Aristotle's theory that air was one of the four essences which made everything was still widely held centuries later. But in the pursuit of industrial riches, a new generation of chemists would question everything and consign Aristotle's ideas to history. Antoine Lavoisier was a French chemist. His experiments into the nature of air would lead to the creation of a whole new rainbow of safe, long-lasting colours.
Lavoisier decided that air was made of two substances, oxygen and nitrogen. Air wasn't a pure substance after all. It was a mixture of two.
Importantly, he realised that oxygen was a pure substance. Try as he might, Lavoisier simply couldn't reduce it or break it apart into simpler components. Oxygen wasn't made of anything else. Lavoisier called oxygen an element. The list of elements soon began to grow. Things like copper, iron and mercury, extracted from rocks, had long been known to man, but now they were seen in a new light. It was discovered that they too were elements, and this understanding of the elements would revolutionise art.
Elements, not Aristotle's essences, were the building blocks of the earth. But to understand exactly what elements are, we need to go back to the ultimate geological event, the one that happened before even time existed, the Big Bang. This may look just like a mass of people, but to me, it's the geological past. You see tourists, I see a swirling mass of the first particles. Scientists don't yet know how it happened, but at some point 14 billion years ago, the universe exploded with an enormous bang. It was the beginning of time, and in the next fraction of a second, particles were created. Neutrons, electrons, and protons. It was from these particles that elements like Lavoisier's oxygen would eventually be made. And it's from these elements that industrial chemists would get a whole new palette of colour. With the help of these unsuspecting people, I'm going to show you what happened. Did you get any special colours you want to take?
These balloons represent the basic particles.
There.
Electrons, protons and neutrons.
Okay, so the red balloons here are electrons, the blue balloons are neutrons, and the yellow balloons are protons. And I want you to start swirling around, different directions, moving around.
Sometime after the Big Bang, the swirling particles started to clump together to create elements or atoms. It's now understood that atoms are the basic building blocks of our world.
Okay, I'm now going to start to make some atoms. Proton, neutron, another electron. Okay, so you guys are a gas, you're helium. To make helium into another element, I'm going to need 3 more balloons. So I've got 1 more neutron. Can I invite you in? Mr. Proton in. Now I've got an atom with 3 protons, 3 neutrons, 3 electrons. You guys are another element. You are lithium.
As the universe developed, other elements were formed, like this one, Lavoisier's oxygen. It's got 8 protons, neutrons and electrons.
Right, okay, I need some more though.
Each element is made up of all 3 particles.
1, 2, 3, 4, 5.
But it's the number of protons that make each element a distinct substance.
Protons. So you guys are now oxygen. take a proton away, excuse me, can I move you over here? And our oxygen becomes a completely different element. In this case, it's nitrogen. The Big Bang created 92 fairly stable elements. Unfortunately, Lavoisier never knew this. Poor chap lost his head to the guillotine in the French Revolution in 1794, by which time only 33 elements had been identified. But the search that he started, which gradually found the missing elements, would change the world and art forever.
And it's here in Paris that we can see the results of this quest. Driven by the demands of industry, chemists discovered more and more elements. And once they'd found the elements, they could begin to combine them. Their experiments produced useful and valuable new materials. These fueled the Industrial Revolution and found their way into factories and homes throughout Europe. The Eiffel Tower was built in 1889 for the centenary of the French Revolution. It stands as a celebration of this frenzied industrial change.
The alchemists had begun the processes of unpicking rocks, extracting the stuff they wanted, like mercury and sulphur, and putting it back together again to create something new. Now, by understanding elements, chemists would unpick the whole world. And as they put it back together again, they made practical things like stainless steel, plastics, and medicines. And like the alchemists before them, the byproduct of this quest for wealth was colour.
Here in Paris's Musée d'Orsay, we can see some of the finest examples of the colours created by chemists in their laboratories. These Impressionist paintings today remain many times more valuable than gold.
Artists like Renoir, Monet and Pissarro eagerly embraced the products of the chemist's laboratories. They took full advantage of the bright blues, the greens and the violets, by deliberately placing new vivid and contrasting colours next to each other. The effect was that things would appear brighter in combination than they would have on their own. They weren't painting the world that they wanted, or even the world as it really was. It was how they felt about it. They wanted to bring their emotions, sensations, their impressions to life.
Every year, thousands of us come to wonderful sun-drenched Provence to enjoy the beautiful countryside and charming towns. These same sites were an inspiration to the next generation of French artists. Van Gogh, Gauguin, and Cézanne. They turned their backs on the city in their quest to paint the world they loved.
By the late 19th century, about 70 of the elements had been discovered, including some of which, with the help of modern chemistry, would prove to be the most colourful of all. Ironically, the post-impressionists used the byproducts of an industrialised and grimy world to paint a completely different world, one that was rural and unspoilt.
Fortunately for us, Provence has remained as they'd have wanted, unspoilt. A place where we can still escape to, if only for a few weeks a year. This is Arles, a Provençal town made famous by Van Gogh and Gauguin. They embraced the town and immortalised it in their paintings using vivid, exciting colours made from a variety of the newly discovered elements.
1797, a French chemist called Vauquelin took a rock discovered in Siberia and extracted a new element, chromium. It turns out this new element produced a bright new paint, chrome yellow. Artists like Van Gogh loved it, and they used it to paint some of his most famous paintings, like the sunflowers and this.
The Asylum Garden at Arles. And this view was painted by Van Gogh's friend and fellow artist Gauguin in 1888. To paint these trees, he used a red pigment made from one of the new elements, cadmium. And for the soft blue sky, he chose another, cerulean blue.
Of the 20 colours regularly used by the Impressionists and Post-Impressionists, 12 were thanks to the discoveries of modern chemistry. So when we look at these paintings, we're not just looking at great art, we're looking at the results of a revolution that started with Lavoisier and his oxygen. But what nobody, not the chemists or the artists, the alchemists or the ancient Egyptians, understood was what makes rocks colourful in the first place.
Where is colour from? Where do we get it made?
What? Color?
How do you make colour? Where does it come from?
Oh, color. Oh, Disney World. Disney World has them. What?
Disney World.
They own the colors.
Color is an expression, I would say, of your personality.
All right, just colour, any colour, anywhere. How do we get it?
In Africa, perhaps.
Could be.
Color is amazing. It's something that you see. It's something that you feel.
Yeah.
Color just runs through your veins.
I used to know the answer. I studied this.
Your teacher is now going to be very upset.
Maybe not necessarily God. Maybe a certain figure sees it as an emotional structure.
Right. I'm kind of baffled. It's a difficult question, but by the time the Impressionists were experimenting with their vivid colours, scientists were beginning to find the answers. They included a Russian chemist called Mendeleev. He used playing cards, one for each element. By arranging and rearranging them into all sorts of possible combinations, he worked out how to fit them into a table so that the elements with the same chemical properties were grouped together. There were question marks on some of the cards because he knew that there were still more elements waiting to be identified.
Each column is like a family of related elements, sharing similar traits and characteristics. And it's this arrangement that was the basis of the modern periodic table. This table is the key to unlocking all the materials of the Earth.
By organising the elements into this table, Mendeleev also helped chemists understand where colour actually comes from.
Here's iron. Mixed with oxygen, this gave the cave artists a red ochre, iron oxide. And here's copper. Volcanic processes turned this into the ancient Egyptians' green malachite. And here is Van Gogh's yellow, chromium. Now look at this. All of the materials that made our colourful paints come from the same part of the periodic table. They're from the same family of metals. Now these elements have got the same protons, neutrons and electrons as all the others. But in this particular family, it's the behaviour of the electrons that actually creates all that bright and wonderful colour. But to show you what I mean, I need to wait till it gets dark.
Colour actually comes from light. Without it, as we can see, once the sun sets, the world's a very dull place indeed. In the 17th century, Isaac Newton shone daylight through a prism and saw this. He had argued that daylight is actually made up of a rainbow of different colours. Newton had discovered that each ray of light from the sun was in fact made up of 7 basic colours. Each one of these colours, like radio waves, had its own wavelength. This is where the electrons and pigments are important.
What scientists in the 20th century finally realised was that it was only when white light, daylight, falls onto something whose electrons can absorb the energy the light contains that we see colours at all. However, those electrons are picky eaters. They only have appetites for light of a particular wavelength or colour, and those appetites vary from one element to another, which is where our rainbow comes in.
Imagine something painted yellow. When the white light falls on it, the electrons in the pigment pick out the yellow from the rainbow of colours and reflect it back. That's why you see yellow. All the other colours contained in the light are simply absorbed.
When you look at this yellow wall, you're actually seeing the only part of the rainbow that's left. The yellow light waves that are being reflected.
What chemists realised when they looked at the periodic table was that a certain group of the elements, the ones in the middle, that they called the transition metals, have particularly colourful appetites.
The electrons of these elements can absorb some of the colours contained in the rainbow, but it's the other colours that they reflect back that give the transition metals their colour.
And that's why the periodic table was so useful to chemists when it came to creating colour. Chemists finally understood which rocks were likely to produce colour, but also why they were so colourful in the first place. We began with just a few shades, but our quest for colour has ended with an almost infinite number of pigments. Over thousands of years, we've learned to manipulate the earth, first by scraping and gathering rocks from beneath our feet. Later, by cooking up recipes using guesswork. And finally, through an understanding of how the world is made, we began to combine elements. At last, the Impressionists and the artists that followed were free from the constraints of a once limited palette. A relationship had developed between geology and chemistry that would help art revolutionise itself time and time again. That is the way of art, to find opportunity through technology. And all this so we can meet our instinctive need to recreate the world around us in glorious, vivid colour.
Which is all amazing, but I still can't paint.
Tonight, the return of Dinner with Portillo, sharing memories and debating the legacy of the post-war years. That's in half an hour after The World. Next.
For further information on Open University programmes, please go to open2.net.
And there's an in-depth exploration of the geological history of the Mediterranean in this book to accompany the series.